the current issues. Thank you.
Thank you. So I thought I would talk today sort of in an overview way. So I'm actually not going to talk in depth about any of my work, though I'll mention some of it. I'm giving you sort of an overview of the field from a particular lens, I guess. And I should also say I've sort of geared this talk to be, I wouldn't necessarily quite say non-technical, but perhaps like less technical than a traditional computer science talk. My hope was to appeal to a sort of a broad audience, which is what I'm guessing you are. So I wanted to talk sort of about the work that came out of this really excellent work by ProPublica that was from May 2016, right? So it came out just under 2 years ago. And since then, it has spurred a huge amount of work in the field, right? Which also means that it's a nice sort of case study to use to try to understand the different algorithmic techniques that have since been developed. So I wanted to start by sort of talking about this nice paper by ProPublica, and then we'll sort of get into some of the more recent technical work that it's spurred on. So this work is about trying to understand what's going on with the risk assessment. So it's specifically a risk assessment called COMPASS that's developed by a company called Northpoint. And let's just sort of look at what a risk assessment is first. So the idea is that in this case, someone is arrested, and the arresting officer fills out some paperwork that looks like this, but it actually goes on for many, many pages. And they fill out, you know, what are the current charges? Was this person on parole at the time? What's the number of previous charges that they have? And so on, right? So a bunch of data is collected, often by hand, right, on a piece of paper, or potentially then manually entered into a computer. Then COMPASS gives a predictive risk assessment score that tries to say what they think the likelihood of recidivism is. And so recidivism, we think of broadly as the likelihood of recommitting a crime, but of course it's actually measured in a very specific way. And in this case, it's usually measured as a rearrest within 2 years. And so they give these decile scores in a bunch of different categories. The one we're generally going to be talking about is the overall recidivism, but you can see that there are many other such things, and a lot of these analyses also apply to those. And they're broken down into these 10 buckets, but they're also broken down into low, medium, and high risk that are sort of groupings of the buckets. And analyses have been done on sort of both ways of thinking about the result. So ProPublica looked at a bunch of people who had been measured by this tool in Broward County in Florida, and then looked at whether or not they actually recidivated, right? Whether they were actually rearrested within 2 years. And they started off by talking about a bunch of individual case studies. And so here we have Vernon and Risha. And Vernon was rated a low risk by this particular COMPASS risk assessment. And then we find out that he did in fact go on to reoffend with 1 grand theft arrest. And then we also have Risha, who was rated a high risk, an 8, and did not go on to reoffend. And of course, these are just 2 examples, right? And the question that they were actually looking at is this a pattern, right? So what you'll notice in each of these examples is that the tool failed, right? So in both of these cases, the tool got it wrong. So Vernon was rated as low risk, but went on to reoffend. Risha was rated as high risk, but went on to not reoffend. So these are both failure examples. And they're failures in different directions, right? And you'll notice that the failure for the white man failed in the direction you would want it to fail if you were the person being rated, right? He sort of got the benefit of the doubt, and the black woman did not. And so then the question was, is this actually a pattern? Right? And what they found is that type of failure was in fact a pattern. Right? So African Americans were twice as likely, about twice as likely, to be labeled high risk but not reoffend. Right? And white people were about twice as likely to have the opposite effect, right? To be labeled low risk but go on to reoffend, to get that sort of benefit of the doubt. Okay, so they found this. This was a big deal when they found it, right? They went on to be finalists for the Pulitzer Prize for this work and related work. But I think in terms of the research community, one of the most important things they did with this work was release all of the data, right? They were very, very transparent about exactly how they found all of this, right? Even though it took them, I believe, years to gather all of the data and have all of the FOIA requests be returned and so on, they still made it freely available afterwards, which meant that people could replicate their analysis and also ask more complicated follow-up questions. And so it's through that lens of those interesting follow-up questions that we're going to think about this field. So one of the core questions that this ProPublica work brings up, and that a lot of other work in the field has also brought up, is are these decisions fair? So is it fair that there's this differential way that this tool fails based on race? And of course, this is a question that's been looked at not just in computer science and machine learning, but in philosophy, in law, right? People have been arguing about what it means to be fair for hundreds, if not thousands of years. And so our goal here is to come up with some mathematical definition that we can test on a data set, right? And on outcomes from a machine learning model, which necessarily limits the nuance in such a definition, but also makes it actionable. And so one place that I've found useful in my own work for finding such definitions that are actionable, right, is the law. So there's this interesting Supreme Court case from 1971, Griggs v. Duke Power. And the idea, what happened in this case is that Duke Power Company had a history of not hiring Black workers. And then the civil rights movement happened, various laws that I don't totally understand put into place, and they were no longer allowed to do that. And so what they did is they said, okay, well, that's fine. We'll just require a high school diploma. And in the place where they were located, that was almost a perfect proxy for race. And so, you know, they got to sort of go on only hiring white workers.
So did this become Duke Energy?
I have no idea. I'm sorry. Maybe. So then this went to the Supreme Court, right? So the workers who were not hired sued. It went to the Supreme Court, and the Supreme Court said, no, you're not allowed to do this thing that might be facially neutral, but in fact has disparate impact in the outcomes. And they referenced this Aesop's fable of the stork and the fox, right? So in this little picture, the stork invites the fox over to have some milk and puts it in that sort of large, like long-necked chalice, right? It's facially neutral, but of course, right, only the stork can actually drink from it, and then the fox retaliates in kind. But the thing that I find really useful about this from a machine learning standpoint is that it's a very outcomes-focused measure, right? It says we don't actually have to go into necessarily understanding all of the reasons behind how the decision was made, but we can look at what the outcome is, and if the outcome has this disparate impact, then we know that it's worth looking into, right? Now, I should say, my understanding is that the law is not cut and dry. It's not that, you know, oh, we see this disproportionate impact and so suddenly it's illegal, right? There's then steps to think about, okay, is that necessary? How did that come about? Is there some other way that you could have the effect that you need without having this disparate impact? But I think usefully, it is a statistical test that you can enact to try to figure out if you should be worried about something. And that specific way of measuring whether there's disparate impact that often goes along with the words disparate impact comes from the EEOC. And so the EEOC has this guidance that's called the 4/5 rule or the 80% rule. And the idea there, the sort of high level goal is that people who apply to a job should be hired at approximately the same rate, regardless of their race. And it's important that it's approximately the same rate and not exactly the same rate, because of course you might have a slightly small company or a small pool of people, and it might not actually be possible to have exactly the same rate. And so they have a little bit of sort of wiggle room in that, and that's where the 4/5 part comes from. So taking that specific measure of disparate impact, this 4/5 rule, I have some work that tries to look at how you can detect whether there might be disparate impact under the 4/5 rule in a machine learning system, and then what you can do about it. And in this context, right, if we're going to formalize what we mean by disparate impact, what we mean here is that we want the probability of receiving a good outcome, given that you're a member of the unprotected class, of the unprivileged class, divided by the probability of receiving a good outcome, given that you're a member of the privileged class. We want that to be close to 1, right? In this case, we're okay as long as that ratio is at least 0.8. So that is one way of codifying it. Thinking back to the compass example, right? In the compass example, it would pass this test, right? So one of the results that I didn't describe from the ProPublica article is that actually, while there was this seemingly unfair result in the way that the errors played out by race, on the positive side, right, they were receiving both high risk and low risk classifications at about the same rate, if you consider an additional question of if you consider whether they recidivated or not, right? And so this doesn't quite capture that. So this is one of the definitions that had been sort of considered a standard way of testing it until the ProPublica article came out. And that spurred a lot of reconsideration because this didn't quite capture the unfairness that was found there, right? So some follow-up papers came out trying to address what they were seeing in the ProPublica case. So one nice paper is by Alex Choldakova. And in her paper, she lays out an additional 3 definitions of what it could mean to be fair. So the first 2 are essentially the same, but one is thresholding based on a score and the other one is not. And in these, calibration and predictive parity, the idea is that your goal is that you should see the outcome. So here, Y is the whether they actually recidivated, right? So you should see that someone recidivated, and you should see that at the same rate, assuming that you condition on their protected class status and the score that you gave them, right? In other words, you want your scores to be operating the same way across race. So if you give someone a score of 8, right, and they're white, versus if you give someone a score of 8 and they're black, you want to see the same probability of them actually recidivating. And then this last definition, 3, is the one that starts to capture some of the notions from this ProPublica article. And this is looking at the errors, right? And it's exactly what you might expect, having seen that case study. So what you want here is that you want the false positive and the false negative rates to be equal across groups. Okay, so ideally, we would have all of these things, right? You can sort of look at these definitions and you can say, yes, that feels fair, right? It feels fair to me that people should have the tool fail in similar ways, regardless of what race they are. And so I want all of these things to be true. And so she started off by looking at this, so this is on the compass data, looking at the extent to which the compass scores actually satisfy these various definitions. right? And you can think about this as essentially replicating the work that ProPublica did in a little bit more detail. So on these calibration and predictive parity assessments, so I don't know if you can read the legend up there, but the gray bar are the Black defendants and the orange bar are the white defendants. And there you can see sort of the error bars here, right? So I don't know if the folks in the back can see it, but essentially the error bars pretty much overlap, right? I mean, there's like a small amount of separation, but on the whole, you can say, okay, it's operating the same way across both cases. Okay, so those definitions are good. On the other hand, again, as we saw with the ProPublica work, that is not the case once we get to the false positive and false negative rates, right? So here, right, there is actually a large separation between these two on both the false positive and the false negative side, right? And it errors in the same direction that ProPublica found it to error. Okay, so that's disappointing, right? And then the question becomes, is it avoidable, right? And Alex goes on to talk about this, and concurrent work also by John Kleinberg and some of his colleagues also goes on to talk about this same question, right? They frame it slightly differently, but the result is essentially the same. And what they find is that there's two cases when it is actually possible to have all of these definitions satisfied. One of those is when you have perfect prediction, which in the case of human actions seems pretty unlikely, right? And then the other is when you have equal base rates. And this is the one that I think it's worth thinking about in more depth. So what this is saying is that you can actually satisfy all of these definitions of fairness if the likelihood of recidivism among all of the populations is exactly the same. If there's equal prevalence of recidivating among the populations. In this data set, there is not. It's different. And so the argument of these papers is that it is due to that difference in the underlying base rates that you see unfairness occurring. Because without equal base rates, you can't actually adjust the system so that you satisfy all of these definitions. And this was, I think, incredibly important in an incredibly important realization in terms of moving the thinking forward, right? On how we should think about what it means to be fair. Because of course, what we would like to say is we would like it to be fair and always, all the time, right? But then at some point we have to say, okay, is that possible? And I think that it's especially important here when thinking about the question of equal base rates to again go back to our definition about how we define recidivism, right? So we defined recidivism as a rearrest within 2 years. Now, I'm not a social scientist, but my understanding of the social science literature is that it's fairly well understood that Black people are far more likely to be arrested whether or not they committed a crime, right? So you would actually expect to see unequal base rates if that's how you've measured recidivism, right? And so then I think the question becomes, okay, well, so that's the data we have, right? What can we do about that, right? How is it appropriate to think through these various set of assumptions given bias in the data? So I have some work with colleagues, Carlos and Sorelle in Arizona and Utah, on trying to think through what the underlying assumptions are that people are making in a lot of this work. And our claim is that a lot of the work falls into one of two camps. So we call these worldviews. So one worldview is the what you see is what you get worldview. And the idea there is data is reality. You have some data, and so we're going to reason straight from the data as if it represents the true complexity. And then the other worldview is the worldview of structural bias, where you assume that the data doesn't reflect reality in a specific way, right? So it's not that there's error distributed at random, but rather that different groups of people, for example, racial groups or gender groups, have their data mapped in different ways so that the data that you are seeing is essentially a result of a potentially biased mapping from some reality. And the assumption that we see people making under this structural bias worldview is the assumption that we're all equal. And what we mean by this is the assumption that if we had access to some true underlying distribution, those distributions conditioned on groups would be the same. Right? So coarsely, we would expect people to actually recommit crimes at the same rate. Now, of course, naturally, you would expect that there might also be some compromise view between these 2 points. We haven't actually seen a lot of work on that yet, right? So, part of what we're saying is perhaps it is more nuanced than this, but we do think that it's important that people state the assumptions that they're coming from upfront, right? Which we hope will allow us to then say, okay, if you are assuming the following thing, then the methods that you're using that follow from that either make sense or don't, right? But one of the things that we think is tricky is trying to have these conversations without an explicit assumption of what you believe is really going on with your data. Okay, so that's fairness as a whirlwind view, right? But one of the things that obviously comes up if you're being asked to state your values, and if you want to really interrogate these questions further, is how can you actually interrogate them, right? Can you actually make automated decisions explainable to the extent that you can have lawyers argue about whether or not that was fair without having to understand the nuances of the technology, right? And how can technology help us bridge that gap? So, again, since the ProPublica article came out, there's been a small amount of interesting movement in the legal landscape. So somebody in Wisconsin was rated based on this Compass score and challenged that rating with the idea that he should be able to face his defendant. So he should be able to review the algorithm, and his lawyers should be able to make arguments about that algorithm as part of his defense. But Compass is proprietary, right? So they've been unwilling to release not only what the algorithm is, but even from that long questionnaire, what are the factors that actually get put into the algorithm, right? So not only don't we know the algorithm, we don't even know the features. And so that was challenged. It went up to the Supreme Court of Wisconsin. And the Supreme Court of Wisconsin decided that it is okay to go ahead and use Compass, even though it's proprietary, but that use should essentially come with a warning label. And they outline 4 points that they essentially think should go into that warning label. And I think the high level idea is that courts should have the various limitations of the tool explained to them, and then the judge should be able to take those limitations into account along with the score. Right? The tricky part there, of course, is that it can be hard to fully explain what's going on with the system, right, without having access to that system. And so a lot of work that has followed this has looked into various ways of either fully explaining the system or trying to give humans some other way to reason about the quality of it. So one work that's actually fairly recent from this January that I thought was interesting looks at whether or not people would be able to make similar quality decisions as this tool does. As a way of potentially justifying or not justifying the tool to a judge. Right? So the specific experiment that they set up is that they automatically created these paragraphs from data that they did have, right? So, you know, the defendant is male, aged 25, and has been charged with some specific crime and has, you know, this crime is a felony, and they've been convicted of this number of previous non-juvenile counts and so on. Right? And then the person, I think it was a mechanical Turker, was then asked to respond yes or no, right? To the question, do you think this person will commit another crime within 2 years? And then they were given some amount of feedback. And what this paper found is that these people can guess the outcome just about as well as Compass. So when they pooled sort of a wisdom of a crowd's approach, then it was about the same prediction accuracy as Compass. When they used fewer people, right, then it was slightly lower accuracy than Compass, but similar AUC for those of you who understand what that means.
They look into the false positive, false negative to see whether they're earning.
Yeah, so they did that, and the false positive and false negative rates showed a similar skew to what Compass found, right? So essentially, within all of these numbers were not exactly the same as the analysis on Compass, but they were all fairly close, right? So you could sort of argue that these people, given this paragraph, can do just as well as Compass, or, not too much worse. Right? Which to me seems like an interesting way of trying to understand how Compass is doing. Right? Meaning, is it actually adding value? And I don't know what a judge would think about that, right? But I would be fascinated to sort of present this to a judge as part of a set of other things that they were considering in considering the validity of Compass. Okay, so another approach we can think of as sort of a global interpretability view of a model, right? So this is when you want to know in detail how the model made all of its decisions. Now, we don't have access to that for Compass, but it's still worth thinking about how you might do that. If you could convince Northpoint to go ahead and release their full model, would that even help? So in some work that I've done on trying to predict the outcome of chemical experiments, I've worked with some scientists, and because they're interested in the scientific hypotheses, they don't just want to know whether an experiment will succeed or fail, they of course want to actually understand something about the science out of this, right? And so we created this decision tree model, which is shown actually only in part up here. It's actually much larger than this, right? And because my colleagues are very patient with me, they actually went through and tried to look at this model, and the sort of highlighted portions are the scientific hypotheses that they developed, right? But as you can sort of start to see, this is large, and trying to gain an understanding from it is painstaking and requires a lot of patience. This is, for example, not something I would want to present to a judge, right? Who has limited time and needs to make some sense of this quickly. There's been some work on trying to develop interpretable models that actually are short and interpretable that I think is really fascinating. And they've applied it to the Compass model, right? Now here, obviously they're not recreating Compass, but what they've done is they've created a model that maps, from the inputs that they have to the outputs that Compass gave. And the model looks like this. And this, I would claim, is actually short and interpretable. Now, in the last talk I gave on this, there was a lawyer in the audience who said, but are you telling me that that's reasonable? Right? And I'm not. I'm not telling you that we should say, now that we can look at this model, this is a great model. Right? I mean, let's all actually read this for a second. What we're saying is, I'm going to predict your recidivism based on your age range, your sex, and a very small amount of information about your priors. What I think is important about this is that a lawyer in the audience can then argue about it, right? Can then say, I think this is absurd for the following reasons, which seems to me to be really valuable, right? That back and forth and ability to interrogate the model in a real way, to interrogate the actual model, right? And not sort of someone's descriptions of it at a course level seems really valuable. Unfortunately, it requires the cooperation of the model creator.
Yeah, just one clarification. For instance, certifiably optimal. What is optimal here?
Yeah, so it's a technical point within the paper. But what they're saying is that of all of the rule lists that take this form, the one that they are generating has the best accuracy on the training set.
So they try to.
Yeah, so the paper goes through exactly how to efficiently explore the space of possible rule lists that look like this. Yeah, I think importantly, it is not saying that this is an optimal model over all possible models. It's not saying that. Okay. Yeah.
Do you think it's possible to distill all the algorithms we use? Like, for instance, you wrote a paper on the predictive policing algorithm, and you use a fully observed model. You take it and you take stochastic analysis, really, you make it into a martingale to show that there's bias in some way. Like, there's no way you can distill that into if-then statements.
Yeah, I mean,
It's great work, by the way.
thank you. I think that, so I agree with you. I'm not totally convinced that, you know, all situations are going to be amenable to, you know, a beautiful interpretable model like this one, right? I think that it is worth the research energy to figure out how to do that as much as possible.
Yeah.
Right, is I guess the argument I'm making. And I think that I would want to see policymakers argue really carefully about situations when a non-interpretable model is applied. Right, like I think that there should be a higher bar for that application and for the evaluation of such a model. And so there's like a sort of a raging debate within the interpretable ML community and sort of from people adjacent to it about whether it's worth creating interpretable models or whether we should continue to focus on accuracy metrics, right? And because those accuracy metrics are better if you have access to the entire world of models instead of some subset of it, that should potentially be enough of an argument to use them, right? And I think that I'm not convinced by that in scenarios that are high stakes human decisions like risk assessments, right? I think that unless those metrics are, you know, far, far, far better than they are or really ever could be, given the sense that you're predicting into someone's future, whether they'll recidivate or not, I think that my opinion is that it's irresponsible to use those because there's no way for a lawyer to responsibly represent their defendant in court against that.
Even if we're an open source model?
So I'm going to use that as the transition to my next section. Is it okay if I go on and then we come back to the broader debate? Because there is another point that I think is really important here to bring up, which is the auditability of these decisions, right? And this gets to this question of, okay, so suppose that you can't perfectly understand the logic of a model, right? You're using a deep net, it works, you think great, but you still want to know something about what's going on in there, right? Is there a way, or potentially you have a proprietary model, it's a black box and you are not allowed access to it. Is there some way to still interrogate that model and be able to say something about what it is doing, right? There is, and there's a couple of different ways about thinking about what you want to do. And I should also say, by the way, my opinion is that there hasn't actually been as much work on this sort of you know, leg of the three-legged stool as there needs to be, right? Like I hope to see actually a lot more work in auditing algorithms and developing techniques to do that. So one such technique looks at trying to determine whether specific features had influence on the result of the model. And here they're looking at direct influence, meaning if I don't give you access to this feature, will you change the result of your classification? Right? And that's exactly how they go about doing this work, right? They take the original data, send it in, find out what the accuracy on that data set is, and then they randomize one of the features, send the data back in, find out how much the accuracy drops. That differential is considered the influence of the feature. There's other work that does actually something similar. that also has this, this nice visualization of the results, right? So this is on a recidivism prediction data set, but it's not the COMPASS data set. It's a slightly different one. And you can see on the top, there's all of the features, and they're looking at essentially the amount of influence, right? Again, sort of under a randomization procedure like the one I just described, of each of those features on the outcome of the model. And then they also look at that for an individual, right? What's the influence of the feature on your individual outcome? And so this gives you some sense of the influence, but it doesn't necessarily give you some sense of how it was influential, right? Perhaps understandably, right? Because it's tricky to figure out how to interrogate the black box in that way. So what you end up with here is you can imagine it as a ranking of the features or a quantitative evaluation of the importance of the features to this black box. You should also note that this technique requires you to have access to the black box, right? So that you can try out sending a bunch of inputs in. All of the techniques actually that I'll be talking about here require that.
So just clarification, this is a binary output like this, or are you trying to do something more?
So in this case, it
Can
was.
you repeat the question, because online?
Oh yes. Was it a binary outcome? So yeah, I believe in this case they're looking at, again, sort of yes or no recidivism within 2
So I
years.
guess I don't know how it influences. You see that it influences, it goes up, you know what it does. You said we don't know how it influences. We know it influences, we don't know how.
So what I mean by that is, so suppose that you are predicting recidivism and you are predicting that someone is likely to recidivate, right? Your current prediction on that person is yes, right? And then I tell you that drug history had a large influence on you saying yes. I haven't actually told you if it had a positive or negative influence on you saying yes, right? Because we have some social understanding of that, we might assume that the drug history made you more likely to say yes, right? But I haven't actually said that. I've just said it has a large influence on.
I think that paper does.
You think it also does do the sign?
Yes.
Okay.
You can discuss it offline, but-
Yeah, we should please do that because I must have just missed that in the paper. Okay, so the next thing, which is actually what some of the work that I described in the interpretability section was really doing, is that if you have the outcomes of a bunch of models, then you can try to model the model, right? So you know what their labels were, you know what the true labels were, you know what their labels were. You can just try to predict their labels, right? So that you can try to sort of mirror what their model is doing. You can model their model, right? And that's actually what we were doing here. We were using a more predictive algorithm to predict the outcome of the chemical experiments and then trying to use the decision tree to explain what that model was doing, right? And it's also what the rule-less work was doing, right? When they were looking at the COMPASS outcomes and trying to predict those, what they were essentially doing is modeling the model, which is a nice way to get something that's interpretable if you don't have access to the true model. The danger, of course, is that you then will look at that interpretation very closely, but it wasn't actually the original model, right? So you have to maintain some skepticism about whether your model of that model is representing the true reality, right? In sort of the chemistry work, we were able to validate the scientific hypotheses separately, right? Which allowed us to verify that it made some sense. And then the last version of this that I wanted to look at thinks about the question of indirect influence. So in the previous influence, feature influence versions that I was talking about, we were talking about what I would term direct influence. And you can imagine this as if you have some decision tree, the question becomes, is there a node in the decision tree that says, you know, if this feature, then do this, right? Is it directly influencing the model? But there's also, I think, especially when you're talking about questions of fairness, a really important question about indirect influence, right? You might have some node in the model that says, if this person is in this zip code, do this other thing. And because we know that zip code is highly correlated with race, you might effectively be using the influence of race to determine your outcome, And a direct influence audit isn't going to pick that up, okay? Unless you then go ahead and test for zip code and sort of do the side calculation to figure out that they're correlated and so on, right? And so our technique was then trying to figure out, okay, how do we audit for the amount of influence from these potential proxy variables without just randomizing all of the variables and getting rid of any information the model has, right? You want to do this in a somehow minimal way. And the insight here is that you can estimate the information content of the feature by trying to predict it from the remaining data. And if you can eliminate this ability to predict that feature, then you've eliminated the information content of that feature in your data set. And we have some previous work sort of proving that, if only a statement. And so the way that we then do this draws on our previous work on disparate impact. So if you have these two marginal distributions in my little story example here, it's men and women's scores on the SAT. And those are the red and the blue distributions. And if we then actually change the underlying data so that both of those marginals are at that center black distribution, then we can't predict whether someone is male or female from looking at the black distribution because it looks the same for both men and women, right? Which means that we've removed that information, right? So if we take it out of just focusing on gender and we think about any feature, if I do this to each feature, right? So I've now sort of picked a feature that I want to remove the information of. In this case, it was gender, right? And I have some other data. In this case, it was SAT. And for each feature pairwise, I can remove this information, right? And then that leaves me some predictive value, right? So I do still have a distribution. I didn't just sort of randomize away all of the information about SAT, but I've removed the piece of it that I want to know the influence about. And then we can do the same trick that these other two papers did of running the model with the original data and then running the model with this obscured version of the data. And we can actually do this sort of gradually. So as you move right here, we remove more and more of the indirect influence per feature, right? And these ones that drop a whole lot are the ones that we find were the most influential, right? Now, so this is again on the COMPAS data, but again, we're sort of modeling the COMPAS model here. So there's two different versions of it because we tried out two different models, right? But in both of them, we can see, so these green and blue lines are the juvenile, felony, and misdemeanor counts. And we can see that those were highly influential under both models. And then age is that red line. That's the sort of the next group of level of influence. And race is, well, race and sex are sort of both a pinkish color, I guess, on this projector, so I don't know if you can tell them apart. But race is this one over here and this one over there. And so in the different models, they actually have different amounts of influence, right? So in that part, we can't actually make a determination. Yeah.
Back to the previous, you're describing here, you remove influence of gender case from each variable by itself. But can't it be the case that you look at a pair of variables? Right?
Yeah, exactly. So we are not doing this in a multidimensional setting. There's been interesting follow-up work that starts to do some of that. But of course, you have to be careful about sort of explosion of cross dimensions, right?
But so the technical way you do it is just to average the two conditional distributions. That's it.
Essentially, we're sort of technically taking a median over the arithmetic distance, but essentially it's really just a median, sort of carefully done.
Just to clarify, this is going to be different for every model. So if I have the data and I use the model and I make this, then I have a new model for the same data and go to another.
So the transformation that you do on the data is consistent regardless of model. So you can do it once and then send it into all the models. Now, obviously, the resulting accuracy drop will be different per model.
But given different data, you'd have to do it
Yes.
like, regardless of the model.
Yes, right. So it's a data-dependent transformation, not a model-dependent transformation, which we actually think is nice because then even if you don't have access to the model to look at the model, you can still run this through in a black box way, right? Because your transformation only depended on the data.
So there's a question from from online participant. Are you saying that we isolate the feature when other features will not impact result?
I'm not sure I understand the question.
Yeah. Maybe we'll address that later.
Yeah, I'm sorry. I would ask them a follow-up, but they're not here.
Just a follow-up, so multidimensional, it would depend on the model.
It would depend on.
If you want to do a multidimensional, well, we can discuss that.
Right, so I don't have a good solution to it, but I'm not convinced that it has to depend on the model. But of course, that's like falsification of something that doesn't exist yet. So it's okay. So just to wrap things up, right? Obviously, all of the things that I've talked about that are algorithmic techniques are not only applicable in this case, right? But I think it's a useful case because so many techniques have been applied on it, because the data is available, to try to tease out what our actual goals are in thinking about applying these models and in thinking about our analysis of them. I also just wanted to plug a conference that happened this February that perhaps some of you got to go to since it was at NYU, the Conference on Fairness, Accountability, and Transparency, affectionately known as FATSTAR. And it'll be happening again probably next February. And if you missed it, the videos are all available online. You can go to fatconference.org, and we have a YouTube channel. I especially recommend the 2 keynotes. They were both brilliant. They should be just watched over and over and over again. And with that, I'll say thank you. I do also want to point you to our GitHub. So for those of you asking like, specific implementation questions, if you would like implementations, they're all there. Thanks.
Which is when you were talking about the model that could be explained if AT was running in numbers of priors, I assume that somebody had run that model with race in it, race not making a difference in those outcomes or not. You know what I'm referring to there?
So I think what you're asking is subtle, because part of the question then becomes, is race actually already implicitly encoded into that simple model, right? And I haven't seen an analysis of that on that simple model, but that doesn't mean it hasn't been done.
I have a question referring to the analysis when you're trying to look at the influence of individual features. Right, so if you imagine in a scenario that there are multiple features are so intertwined that removing one won't make any difference. So what you were observing is that nearly none of the features actually matter, right? Would that be the case? Like so I think in statistics we understand information, feature carry information, predictive information, and imagine that 2 features are very correlated, but they carry about the same information. So when you adjust for one feature, the other feature will contribute more information into the predictive model, which means that dropping this feature doesn't make any difference.
So I think, so if those 2 are very closely correlated, then what will actually happen is that both of them will drop, right? So if you remove one of them, it will necessarily remove that piece of the information from the other. So for example, we, to sort of test out the technique, we ran this also on a little synthetic data set where, 3 of the variables were just directly correlated, right? They were just different ways of encoding exactly the same information. And in that, when you removed one of them, right, the other 2 also dropped exactly in line with that one. I don't actually have the figure here, so you're just gonna have to be satisfied with my hand motions, but yeah. So I don't actually think the effect that you're describing would happen. Yeah.
So this is a very open-ended question. If we are the ones building the model, what can we do to ensure fairness?
Yeah. So I mean, it's also a tricky question, right? Because like we were just talking about, there's a bunch of different definitions of fairness, right? So the first thing that you would want to do is think about the specific context that you're looking at and what fairness means in that context, right? I would then also encourage you to try to find an interpretable model that you felt like had high enough accuracy that you could responsibly use, right? But I think the number one thing, honestly, is to talk to people in the domain of the data that you're looking at, because there are often subtle issues that are raised there that you also need to account for that just might not occur to you, right? So if you're given a data set like the Compass data set and it says, you know, yes or no recidivism within 2 years, it might not occur to you that even that measure of recidivism might be biased, right? And you might need to carefully account for that in some way. But if you talked to somebody who understood that domain specifically, that would be potentially an obvious thing that they would bring up immediately, and then you would get to incorporate that into your understanding of what you should be doing.
Yeah, I'm afraid that because of my own ignorance, I may not have followed the argument, and I just want to make sure I understood what to me was you know, really striking when you were talking about the Kleinberg paper.
Mm-hmm.
You know, did I understand you to say that the finding was that unless the baseline rates are the same across groups, that you're always going to have a differential in false positives, false negatives?
Or calibration.
Or what?
Here, so let me click backwards a lot. Sorry. So there are 3 things there that are being balanced, right? And the result is that you can't actually have, there are 3. You can't have all 3 at once unless one of those 2 conditions, either perfect predicted power or equal base rates, is possible, right? So this first one is the one that you were missing. So it's the calibration, right? It was in Alex Shildakova's work, it's this, right? So this is a well-calibrated system, right? Essentially because these bars are about the same level for all of these different deciles. So you can't have that and have the same be true on both of these charts.
And there are unequal base rates.
Right. So essentially, like the course way I think about it is that extra recidivism, or the extra sort of measured recidivism of one subpopulation has to go somewhere.
Yeah.
Right. So it either shows up in a differential in the error, or it shows up in a differential in the calibration. But you can't just sort of magic away that differential, right, if it's in your data.
Right. So, I mean, as a policy matter, would one way of dealing with this be like kind of post-processing, that you would kind of adjust the scores in a way that, you know, would equalize the numbers of false positives and false negatives? Is that, and this is where my ignorance comes in, like, you know, just talking about how, as a matter of policy, if you decide you don't want to have, you know, higher rates of false positives, you know, for one group, that you would manually adjust scores internally.
So the result is that you can't do that.
Yeah.
Right. It's not. Their point was that it's not a failing of Compass.
Yeah.
It's a failing of the data.
Mm-hmm.
Right. And so it's not that if you built a better model, it would be better.
Well,
it's that you actually can't do this.
Right. So what you're saying is that because of the you know, Black people are more likely to get arrested, you know, that is one of the reasons why you have higher recidivism rates. And so, you know, you can't, it's kind of in a way, it's like autocorrelation within the data, right? So, so you can't change the model in a way to eliminate that kind of bias. I guess what I'm saying is, like, what do you do then with the data that you do get, you know, and how you feed those scores to people making these decisions.
And I mean, my opinion is that this is why it's so important to have explainability, right? Because then you could say, okay, well, I'm going to calibrate it correctly, right? And then I'm going to try to be very transparent with the judges about this differential in error rates, right? And explain to them where it comes from and show them what the model is doing, and then ask them to, you know, use their human skepticism right, in this particular way.
Do you also think it could be a problem of like an overdetermined system in the sense of like, okay, like our data is flawed, like, or in the sense that, so we don't agree with what our data gives us, like we don't like it. You know, Black people are more likely to be arrested. You know, so can we make it like zip code and Black blind? Like, do we need all of these variables when we're assessing a person's likelihood to go back to commit a crime?
So-
Or be arrested again, not commit a crime.
So I'm gonna answer your question slightly differently. So I think part of what you're searching for is a way of having better data that doesn't exhibit this problem. And I think one of the things that I would be interested to know more about, which I just genuinely haven't seen the data for, is how much of this disparity goes away, or does any of it go away, if you look at conviction instead of rearrest. Right? That seems to me like that would be a reasonable next step, right? Now, my understanding is that there you now also have to be careful about, was it a plea deal, right, that this person was pressured to take in order to not spend too much time at Rikers, or, you know, was this a jury conviction, right? From what I understand, then the problem also becomes that now you have a very, very small, right, because most people take plea deals. If you want to only look at jury convictions, then your data just becomes a much smaller proportion of the data that you can work with, which then potentially causes statistical issues. So I think there's like a number of trade-offs in trying to figure this out, but I haven't yet seen work focusing in on that. Though again, I'm not a specialist in criminal justice, so it's totally possible that that work has happened in that field.
Well, have you also seen like there was data on, you know, taking like Amazon Turks or whatever, you know, survey of just a random person versus Compass. Compass is kind of meant, right, to replace like a judge, if you will. So like, has there been a study of like, if the judges were given the same data, they would produce the same answer as Compass would?
Oh, that's interesting. I haven't seen that. I don't think
That's what when I saw participant, I was like, what's their background? Like,
Right, yeah.
First question.
So you're saying, what if you make it in fact an expert participant?
Right.
I imagine that would improve it, but I haven't seen a study.
But if it were to improve it, then that would make a case for Compass being a poor algorithm.
Which is, I think, honestly, the case that a lot of this work has been making. Right? Is that?
I mean, it's a very clear one too, though.
Thanks for the great talk. I have any questions, but I just wanted to keep one that maybe more related to what you said. I like this division between, you know, you either trust the data blindly or you trust that this is equal blindly and or something. I'm trying to understand, after you said that, you proposed at the end this iterative inference, which seems to me completely trusting the data blindly. But maybe not.
Okay, so you're saying, how does this sort of worldview thing relate to the question of direct and indirect influence?
Yeah, I guess if you pose this problem and we need to work in both, and it looks to me that I was just wondering, are you going to work in both? Are you doing only the first type of work? I'm just curious because it's interesting.
Yeah, this is, so I haven't actually thought about these two things specifically together, but the work on indirect influence actually comes out of work that assumes we're all equal, right? So it comes out of work that's guaranteeing, these are annoying because they're not right next to each other, sorry. Let's zoom through this. There we go. So this work, the certifying and removing disparate impact paper, is focusing on, so the removing disparate impact part is the sort of widget that you're seeing here. And what that's trying to do is make sure that any model that's trained on this data would not have disparate impact under the 4/5 rule. Essentially, the idea being that we've removed the possibility of inferring that information. So you sort of imagine a malicious model that's doing its best to try to discriminate, right? We've removed the information that it could use to discriminate by gender there. And so therefore it won't, with the sort of multidimensional caveat that we talked about earlier. And so this is actually taking a we're all equal worldview, because what it's trying to guarantee is that people receive outcomes at the same rate, which is a we're all equal measurement of fairness.
But that could be, it could be true that SAT is an imperfect view, and that creates a bias for some groups. But removing it by force doesn't prove that you make fairness to something with a higher order. For instance, it could be that among the groups, there are some particular kind that have high SAT, and those ones would be by this completely discriminated.
Yeah, which way does the discrimination go?
So that's why,
Yeah, so this is,
I agree that if you believe strongly in the we are equal assumption, even if you believe that strongly, that is not going to prove that you're fair.
so, I mean, so this is why we take it as an axiomatic assumption, right? Because
Yeah,
we're,
but I'm saying even if you, okay, we can discuss about that. I think even if you take it, it's not true. But,
that I'm not convinced by. So we should definitely have that discussion.
So I think this will be a good time for us to wrap up this session. So let's just thank our speaker again.